So our second concept is the concept of the intersection between objects. So there are three cases as shown on the slide. The case between the point of intersection between two lines, so we may be interested to find the position vector or the coordinates of this point. A line and plane could also intersect in a point, and we'll be interested to find the coordinates of this point. And for the third case, we have two planes. So given the equation of two planes, they may intersect in a line, and we are interested to find the equation of this line of intersection between these two planes. So we will make use of some examples to run through each of the three cases to see how each of them can be done. But the underlying concept behind each of this is we are trying to solve a pair of simultaneous equations, be it between a line and line, line and plane, or plane and plane. The techniques, however, are a bit different, so let's look at our example to learn a bit more about them. So our first example is the intersection between two lines. So we are given two lines, L1 with this equation and L2 with the other equation. And our aim is to get the coordinates of the point of the intersection between these two lines. So the technique here will be to observe that the first line, the equation is r equals to 1, 2, 3 plus lambda 1, 1 minus 2. And the second line is given by r equals to 4, 2, 0 plus mu 1 minus 2, 1. So both equations have this vector r, so we can equate the two of them. So what we have, if we combine this 1, 2, 3 and 1, 1 minus 2, if we get 1 plus lambda, 2 plus lambda, and 3 minus 2 lambda. Similarly, we can combine these two vectors to get 4 plus mu, 2 minus 2 mu, and mu for line 2. And we will equate these two lines together. This vector equation actually gives us three equations. The first line gives us 1 plus lambda equals 4 plus mu. The second gives us 2 plus lambda equals 2 minus 2 mu, while the third gives us 3 minus 2 lambda equals 2 mu. It seems a bit complicated with three equations, but actually we only have two unknowns, so we can simply pick any of the two equations and solve our usual simultaneous equations to get the answers for lambda and mu. The last equation that we did not use can be used to check our answer, but the purpose of three equations will be more obvious when we discuss section 5 about the relationship between two lines. However, at the moment, let's just solve any two equations, and if we work it out, we should be able to get the answer lambda equals 2 and mu equals minus 1 for this particular example. We can use either of the answers. If we take lambda equals 2, we can plug into our equation of line 1 to get the point of intersection. You can also use mu equals minus 1 in the second equation, and they should give us the same answer. Our second case of intersection is that of between the line and the plane. So now we have a second example. We are given the equation of L1 over here, and the equation of the plane, r dot 105 equals to 7. So in this picture over here, we are interested in the point of intersection between this line and this plane. Unlike in the first case where we can equate the two equations, we can't really do that here because we don't have an explicit formula for r in the equation of the plane. We don't have r equals something. Instead, what we have is the dot product formula, r dot 105 equals to 7. We still want to solve the simultaneous equation, but the technique we'll be using over here is the technique of substitution. We'll take the equation of the line over here, r equals to 1, 2, 3 plus lambda 1, 1 minus 2, and substitute this into the equation of the plane. So this is what we have. We have 1 plus lambda, 2 plus lambda, and 3 minus 2 lambda. That's the equation of our line. Dot with 105 equals to 7. So we sub the line into the plane. Working out this equation, working out the dot product, will allow us to solve for lambda. So for this example, you should work it out and get the answer lambda equals to 1. After finding this value of lambda, we can plug it back into our equation of the line to obtain the coordinates of this point of intersection between the line and the plane. So for this example, our point of intersection is 2, 3, 1. So our last case in this concept of intersection is that between the plane and the plane. So we have two planes in this example, P1 and P2, and we are given the equations, and our aim is to find the equation of the line of intersection between the two of them. So this can be a pretty tricky concept, and there are a few methods to do this. For our video, we're going to make use of a graphing calculator, the TI-84 series of calculator, with the software included in the Singapore version of the firmware of the calculator. There is another method to do this without using a graphing calculator that uses vectors as well as a bit of algebra. So for that method, for that alternative method, I will write out a blog post and I'll post a link to that in the comments below. So if you're interested in the alternative method that doesn't make use of the TI-84 calculators, you can go over to the blog post to have a look. But for now, we will try using our graphing calculator to solve this question. Our calculators don't handle vectors very well, so currently the equation of the planes are in the scalar product form. So instead, we will convert them to Cartesian equation x, y, and z, which our calculators are better at handling. So our first equation of the plane, r.105 equals to 7, we will convert them into Cartesian equation, x plus 5z equals to 7. We will do something similar for plane 2, getting our equation x plus y minus z equals to minus 3. So we have two equations over here, but 3 unknowns, which makes it tough to solve by hand. So let's go over to our calculator to see how this can be solved. So on our calculator, we'll be looking for the EPS button. So on this calculator, it's over here, and the EPS. And when we click it, then we have a list of apps on our calculator. You may have a different list for your calculator, but the app we are looking for is this app called Poly Simultaneous 2. So hopefully this is on your calculator as well. So let's click enter to enter. We're solving a set of simultaneous equations. So let's go to option 2, simultaneous equation solver. For our two planes, we have two equations and 3 unknowns, x, y, and z. So let's change some of the options. Equations, we have 2 equations, and unknowns, we have to change over to 3 unknowns on our calculator. After we are done, we go to next, and that's available on the 5th button over here, the graph button. So when we go next, we'll be asked to key our system of equations. Our first equation is x plus 5z equals to 7. So our coefficients will be, the coefficient of x is 1, followed by the coefficient of y, which is 0, and finally the coefficient of z, which is 5, and our constant, which is 7. Okay, for our second equation, we have x plus y minus z equals to minus 3. So the coefficient of x is 1, the coefficient of y is 1, the coefficient of z is negative 1, and finally the constant is negative 3. Oops, I forgot the extra negative. So the constant is negative 3 as shown over here. Okay, so when we have keyed it in, we go to solve, which is the 5th button again. And our different calculator will give us this solution. It looks a bit weird. 7 minus 5 x3. So what does x3 represent? So the trick to tackle this question is to observe that what we want is the equation of a line. How does the equation of a line look like? It has a point plus lambda of a direction vector. So there's an unknown lambda within our equation of the line. So when our calculator says x3, one way to interpret it is we can treat x3 as if it's lambda. So let's translate it into our answer. So notice the first equation is 7 minus 5 x3 on our calculator. That can be translated on the first row as 7 minus 5 lambda. Our second answer in our GC, x2 equals to minus 10 plus 6 x3, can be translated as negative 10 plus lambda 6. And finally, x3 equals x3 can be translated as our last row, 0 plus lambda times 1. So this is how we interpret our answer from our graphing calculator. We split up the numbers without x3, that's our point, 7 minus 10, 0 is our point. And when we see x3 in our calculator, the coefficients of it give us our direction vector. So the coefficients of x3 is minus 5, 6, and 1. That's our direction vector, minus 5, 6, and 1. So this is how we can use our graphing calculator to help us solve the case of intersections between two planes. So to summarize this concept of intersection, our aim is to solve simultaneous equations between lines and lines, lines and planes, as well as planes and planes. Each method is a bit different. For lines and lines, we are equating our two equations. For lines and planes, we are substituting the equation of the line into the plane. And for planes and planes, we will be using our graphing calculator.